We've done a fair amount of number theory fundamentals, including divisibility and modular arithmetic, but then remember that we are studying cryptography, so how does this exactly apply to cryptography? Well, first thing is the Caesar cipher, right? If we think about the Caesar cipher, we're taking a message and shifting it by a certain amount, and then in the event that we're at the end of the alphabet or whatever, and then we need to go to the beginning, right? That idea is modulus, and specifically when we're working with Caesar cipher, typically we're working with mod 26, or equivalently, we would do z mod 26z. Okay, so and typically how people work with Caesar ciphers are that they identify a number with every letter. So 0 is A, 25 is Z, and then you add everything. You add your shift amount, great. Mod 26, great, and then convert it back. Okay, another application that we will see in the future is that specifically with RSA and Diffie-Hellman, is that we will sometimes need to compute a number g that has a large exponent on it, such as 5 to the 623, and then do it in mod m, where the modulus is pretty large, so 1200. Okay, this is small-ish, if you can actually believe that. And then so I want you to think how you would do this. I have thought of 3 ways. And we'll go ahead and talk about those in a minute. But go ahead and think about how would you tackle this problem? How would you do this calculation? Okay, well, hopefully you did a little bit of thinking. And first way, and I'm sure your first gut reaction right now is to use a computer. And I will say yes, Wolfram Alpha is also capable of doing this. Okay, but keep in mind that with this, you're relying on technology. So in the event that you don't have access to technology, what do? Well, then that's where you have to think of the other 2 ways. First way is just repeat or successive squaring or successive exponentiation. Okay. So this is to say you start with something like g, and then you do, this is equivalent to g1 mod m. Okay. Then, so you reduce it mod m, then you do g1 times g, and then this is going to be equivalent to g2 mod m. Okay, so reduce it, and then multiply and reduce, so this is in essence g squared. And then you do g2 times g to get g3, so this is really g cubed, and you do that mod m, and continue on and on and on, and do this forever. Is this efficient? No. Yeah, that's like the least efficient thing that's possible, but it'll get you your answer. Okay. The third route is something that different textbooks call it different things, but I know it as fast exponentiation. Okay, so you're still going to have to play with exponents, but it's a little bit faster. Okay, and the idea is that you start with whatever your exponent is, and you write it in terms of powers of 2. So for example, this number, 653, can be written as 512 plus 128 plus 8 plus 4 plus 1. Okay? Which, in terms of powers of 2, is 2 to the 9th plus 2 to the 7th plus 2 to the 3rd plus 2 squared plus 1. Or plus, and actually that'd be 2 to the 0. Okay? And so then what you do with that breakdown is you return to your original problem. So 5 and then 653, okay, is equal to 5 to the power of 2 to the 9th plus 2 to the 7th. I'm just substituting here. 2 to the 3rd plus 2 squared plus 2 to the 0. Okay, and then, by laws of exponents, we know that we can break this down as 5 times 2 to the 9th times 5 times 2 to the 7th, and then plus 5, or times 5 times 2 to the third times 5 times 2 to the second plus 5 times 2 to the 0th. Oh, not plus, times. Okay. Alright, so I haven't done any modulus anywhere yet. Okay. Then, now, what we have to recognize is that these all appear as like 2 to the I, right? So then now, what I can just kind of think about in the back of my head is that if I make this table, okay, I have an I for a power, and then I'm going to have 5 raised to the 2 to the ith power. Okay? And so then I can make a table 1, or 0, 1, 2, 3, and I'll need to go up to 9. Okay? 4, 5, 6, 7, 8, 9. Okay? And then I can compute 5 to the 2 to the I. Okay? When I put in 0, this is just going to be, okay, so it'd be 2 to the 0 is 1, so 5, and then 2, so that'd be 25, and then 2, so that'd be 2 to the, let's see, 2 squared, which is 4, and then 5 to the 4th is 625. So this idea, when I do this, is the idea of successive squaring. Okay, and then I'm going to have you pause the video and complete the rest of this table, and resume the video when you're ready. Okay, and so maybe you completed the table, maybe you didn't. What you should have noticed is that 3, you get like, what, 390,000-ish? Big number, right? So wouldn't it be convenient if, we know we have to introduce a modulus anyway, wouldn't it be convenient if we just did mod 1200 to begin with? And so then our life becomes a little bit easier when we do that. So so again, from 5 to 25 I squared it, 25 to 625 I squared it, so the next one would be 625 squared mod 1200, and when I do that I got 625. And so then that's going to be the same for the rest of these. Now the only thing I'll say is generally it's not going to be this nice, okay? It just happened to be the number, or the example that I picked. But so then what I would do from where I am at here is that if I simplify this from where I left off, this would be congruent now, since I'm introducing modulus, to 625 for the first one, 625 for the second, and then 625 for that third. Oops, 625, not 253, 625 for the 5 to the 2 to the third, and then for 5 to the 2 to the second, be 625 for that, according to the table, and then for 5 to the second to the 0, that is going to be times 5, and then I have to do all this mod 1200, and this is quicker for me, so this is 625 squared, and this is 625 squared, and then both of these would become 625, and then times 5 at the end. So then I just have to do that mod 1200, and what I should end up with is 725 mod 1200. Okay, so you can see that this method is already faster than the previous one, certainly not as fast as a computer, but it could still work should you need to. So we'll get some practice with this in our in-person time, and that concludes the videos for this week.